This year is that we start looking at electrochemistry. What electrochemistry means is the link between oxidation reduction and generating or using electricity. We use oxidation reduction to make cells or batteries. Okay, so the batteries you put in your cell phones and your calculators, those sorts of things. The proper physics and chemistry name for that is a cell. By the way, in your car it is called a battery because it's a series of cells next to each other. These all rely on an oxidation and a reduction reaction occurring. And one of them absorbs electrons or attracts them, so that would be your reduction reaction. And so that would end up being the negative terminal, sorry, the positive terminal, because it's the electrons that are being lost, are being gained there. So being attracted to that terminal because it's positive. And it creates the negative terminal of your cell where they're being lost, the oxidation's occurring and being given off. And so what we're going to do in the next week and a half is we're going to learn about the link between oxidation and reduction and being able to create a voltage. Okay. So one of the first things you need to understand about for that is a thing called the Standard Electrode Potential. Now at this early stage, I want you to think of it as something like electronegativity or ionization energy. Don't worry too much about how it's worked out. We will get to that later. I just want you to think of it as a scale, okay? And it goes from very positive to very negative, all right? How it's worked out we will do in a later lesson. But just think of it this way. It's a scale. Something up here is a much stronger oxidant than something down here, and things in the negatives are reductants, or usually act as reductants. Usually, not always. We'll get to that in a moment. So it's the relative ability of a species, so that can be an ion or an atom or a molecule. That's the word we use for that's what a species is, to act as an oxidant. So if the number is very big, it's a very strong oxidant. Now, and if it's very low or even negative, it's a weak oxidant or could even be a reductant. Last year, a lot of you probably did physical science, where you probably looked at the activity series of metals, and, sorry, not last year, 2 years ago, and you would have talked about certain metals being more reactive than others. And I think if we think common sense-wise, sodium is more reactive than magnesium, magnesium is more reactive than iron, iron's more reactive than silver, for example. This is actually not to do with reactivity per se, this is actually to do with their ability to be oxidized. Sodium has a very, very negative electrode potential. It's very difficult to reduce sodium. Sodium ions back into sodium. They're very difficult. It actually, whenever you react sodium with just about anything, the sodium metal will turn into iron, so the reverse reaction will occur. It will be oxidized, so it will be a very strong reductant. By the same sequence that was done, magnesium would probably be about here. Iron would be about here. Silver's probably up here somewhere. So this actually has a link to what you might have called the activity series of the metals. But we're not just talking about metals, we're talking about permanganate, we're talking about hydrogen peroxide, we're talking about iron 2 turning into iron 3, or vice versa. So it's more than just metals. Right. So because this tells us how strong an oxidant something is, there's another word that chemists commonly use for this, which I actually think makes more sense than an electrode potential. That's more a physicsy type term. Chemists will often call them their reduction potential, which I think makes sense. If it's got a big number, it's got more potential to undergo reduction. If it's a negative number, it's got a higher potential to undergo oxidation. Sort of makes sense? I like this word better. The problem for you is in your assessments, they'll use that word. But it's nice to have those two words meaning the same thing in our minds. When I see electrode potential, think reduction potential. The bigger the number is, the more likely it is to be reduced. Now, I did say that we'd talk about this having a link to electricity, because electrons are being transferred, so there's going to be a current possibly, or there's going to be some link to electrical energy. So what's convenient here is it's a unit you've met before in physical science and physics, that this is measured in volts. Okay, so we use a voltmeter to measure this value when we set up a cell. We can find the voltage. We can actually predict the voltage a cell should give before we even make the cell, so before we even waste any chemicals to do it. But what's really cool about this for chemistry is we can predict if a reaction is going to occur or not. Now this is a different type of prediction to when we used entropy and Gibbs free energy. Okay? They both need to be the correct values. Gibbs free energy needs to be negative, and the electrode potential needs to be positive. If both of these are satisfied, you will have a chemical reaction occur. Okay? Now in the internal, you don't need to talk about Gibbs free energy. I'm just mentioning that to give you the big picture. That if you don't see a reaction occur but it has a positive electrode potential, that might be that it wasn't hot enough, for example, to go at a rate that you could observe. So you might have needed to heat the reaction. Okay? So just be aware of that. You need both for spontaneity, but of course the ones we're going to give you in the internal are going to be able to occur at room temperature. So all you'll be worried about is the electrode potential being positive. So how do we use these values to do any calculations? I've actually got one set up on the other board, which I'll bring across to show you how we use this little equation here, which is on page 49 in your books. By the way, the data that I'm using is coming from page 50 in your books. So if you do want to see what I'm looking at to get these values, it's on page 50 on the far left-hand side. Okay, so the example I'm going to give you here is a reaction that we might have seen before. If I put a piece of magnesium into iron 2 sulfate, then often what I get is, well, I actually get some bubbling because it's often acidic, but I also get a very important colour change. It goes from being green to being colourless, and I start seeing a dark grey or almost black metal being formed, which is our iron. The magnesium breaks apart, it starts to disappear. It might not completely disappear, but it does start to break apart, which suggests to us that it's becoming magnesium ions, which are colourless. I can prove or show why this is spontaneous by using electrode potentials. I need to look at, first of all, which of these is being reduced. Which one of these two things I start with is being reduced? Magnesium or iron 2+, which one is lowering its oxidation number, or in other words, gaining electrons?
Iron.
The iron 2, well done. So, I've got this one here. So, this is the reduction half equation, it's half equations in there. So I can use that number in here. So I put negative 0.47 volts. Then I need to subtract the value for the one for oxidation. So if that's reduction, clearly magnesium must be being oxidized, going from magnesium to magnesium 2+. Notice in these it's written the other way around. It's written the other way around because these are reduction potentials. That to that is the reduction reaction. But the way that I work it out is I just put that negative into here as well. Okay, so negative, that number there, negative 2.36 volts. Okay. When I work this number out, and I haven't done this prior to the lesson, so I might need some helpers on that, please. Negative 0.47 minus negative 2.36. My brain's not doing it fast enough. Is it positive 1.89? Okay, and because it's positive, that affirms or confirms why we do see that reaction occurring. Okay, so it's greater than 0, therefore it's spontaneous. Okay. Now we can also use this to explain, and I'm not going to do this one in the video, I'm going to get you to do this. We can also use this to explain why hydrogen peroxide auto-oxidizes. If we leave hydrogen peroxide in a bottle for any length of time, its concentration decreases because it auto-oxidizes. It oxidizes and reduces itself, becoming, here's where I hope I get my balanced equation right, and I didn't, of course. Okay, so it goes to oxygen and water. In here, you've got two half equations that are possible. One is the reduction of H2O2. What does it become when it's being reduced? Not sure. O2 is the oxidation, but we'll put that one in just a second. So you'll have a value for that one. And you've got the oxidation one there in this case, but that would be the reduction, of course, from oxygen to hydrogen peroxide, adding of hydrogen. So what you're going to be asked to do is to find the values for those and calculate the electrode potential for the entire reaction and see if it is positive or negative. Okay? If you get the negative value, it means that you've got them back to front, to be honest. All right. So that's your next task. Any questions before I stop this? Okay. So just to do a quick recap. Electrode potential is a relative measure of how strong an oxidant something is, so how easily it will be reduced. It's on a scale that goes into positives and goes into negatives. If it goes into negatives, those things usually act as a reductant. However, in our iron and magnesium example, iron 2 plus and magnesium example, we saw that even something that usually is a reductant, is a weak reductant, when it's put with a stronger reductant, it will still react. Okay, and we used to call that our activity series for our metals. We measure it in volts because there is a link to electricity, and we'll see that later when we talk about cells. There is a way to use these values to show or prove or predict that a reaction has occurred, and this is by taking the electrode potential for whatever's being reduced and subtracting the electrode potential of whatever's being oxidized. If that minus that is positive, the reaction is what we call spontaneous, and again, presuming that the delta G, the Gibbs free energy change, is negative.